Welcome to Web Handling. My name is Dave Roysam. I am super excited to continue this new mini-series on core sizing. In this clip, we discuss length. If cores are too short, we can have functional as well as cosmetic problems with our wound rolls. If the cores are too long, we can have even more serious problems. Please see the previous clip which discusses optimization because we will be building on those concepts here. I know your time is precious, so let's get started. Here are just a few of the concerns that involve core length. The first is that the core length will be approximately the width of the wound roll as ordered by your customer. However, as we will see in the next slide, even this is not a simple concept because we must choose whether to have the cores noticeably wider than the roll, as is common in converting, or flush, as is the case for most rolls. Then we must consider core width tolerancing and core CD positioning. Life gets even more complicated when we consider the many failure modes that are affected by length. These include excessive deflection, vibration, stresses on the web product itself, and many others. A core stickout of 2 to 4 inches may be desired for some applications. Sometimes this stickout is used to support the rolls in the saddle in a shipping box. Sometimes the stickout is used to protect the rolls from end damage. Much more common is to have the core as flush as possible to the edge of the roll. A maximum variance could be a tolerance specification, such as the core can stick out no more than 1 millimeter out beyond the edge of the roll, nor can it be as much as 2 millimeters inside the edge of the roll. To support a specification like this, we must consider tolerances for normal variations in the wound roll width itself, core cut width, core moisture during cutting and during winding, and finally, core positioning with respect to the incoming web from the slitters. It would do no good, for example, to specify core to roll edge alignment tolerances of 1 millimeter if, for example, core width varied by 2 millimeters. Economics must also be considered. Tight core width tolerances may require a secondary core cut instead of just a primary cut on the core winder. Tight core width tolerances also may require tight moisture control during manufacturing and even moisture control conditioning rooms inside the customer's plant. An intentional inset is usually not a good idea because it can cause a mini star just above the core. It can also invite roll edge damage due to the chuck or shaft insertion. Wound roll deflection is a complicated subject. First, there may be a tiny bit of support from the core shaft to help resist deflection. However, this support may be zero. For example, if the core deflects 1 millimeter and there is a 1 millimeter clearance between the core and the core shaft. Then there is the possible self-stiffening of the wound roll itself. As the roll winds, the nip load may change, the roll weight increases, and the layers of the roll above the core can cause the roll to get stiffer. Self-stiffening is near zero for the roll that has center slits. In that case, the rolls themselves are simply dead weight and do not contribute much to stiffening. However, none of this is a simple calculation, such as for a simple reinforced concrete beam that some of you may have learned in your college strength of materials class, such as the one I taught. To my knowledge, only one person has ever attempted to model the complexities of the deflection of a wound roll system. Bruce Lindstrand, a good buddy and co-worker when I worked at Beloit, used the services of some high-powered, nonlinear, finite element models to get stresses and deflections. Bruce verified this with measurements. The shocking conclusion was that the wound roll, because it is radially soft, does not deflect as much as the core or the mandrel that supports this. The figure shows an exaggerated version of this behavior. As a consequence, there is a stress concentration on the ends that could easily explain certain defects found just above the mandrel or core at the edges of the wound roll. We will have more to say about pressure-related failures of the web in the next clip. However, even if you could calculate deflection, we would still be totally blind. That is because we have no guidance from the suppliers of winders, core shafts, or cores on what is a maximum allowable deflection. This is quite unlike rollers, where deflection has been used to size most roller diameters for decades. The common 0.00015 times width that is most common for rollers, as well as wound roll mandrels, would be uneconomic for cores. That is because the cores would have to be much larger than the rollers because they are made of cardboard instead of metal. No one can afford disposable cores that large. As a consequence, suffering from excessive core deflection on winders is actually quite common. For some high-speed applications, critical speed is, well, a critical factor. If you exceed that speed and the roller is poorly balanced, it can literally explode. However, if we cannot calculate deflection, we can certainly not calculate critical speed, which is even more complicated due to unwind structural flexibility. Thus, an auto slowdown circuit must be used for safe operation. On the graph of speed versus unwinding diameter, we see a red line for critical speed. It is lower at small diameters because not only is the wound roll less stiff, but also because the RPMs are ever increasing due to the smaller diameter. Thus, the machine must begin a slowdown at the dotted yellow line diameter and stay well below that critical speed, which can be measured but not modeled. Thank you so very much for joining me in this problem solving and problem preventing series based on optimum core sizing. Stay tuned for the next clips where we will talk about failures of both the core and your web product due to stresses that are affected by core sizing. If you found anything interesting or useful here, please like and share and subscribe. See you next time.